Hello and welcome to this video. Today I've got something that I'm super excited about showing you, and that is drawing images on an oscilloscope just using electrical signals. This is an idea that I've been fascinated by for honestly years at this point. Since before I knew anything about electronics or low-level programming, I saw some demos of people basically syncing up music to cool animations on an oscilloscope, and I was kind of just like, it blew my mind. I didn't really understand how it was possible. Today I'm going to actually walk you through the whole method of how you do this, and we're going to write the firmware together for a little microcontroller so that we can actually do exactly this kind of thing. And I think you're going to be surprised at how simple it actually ends up being. And one of the coolest things about this whole demo, and I'll show you the electronics for this in a minute, but one of the coolest things about this is it's literally just a microcontroller and 4 passive components, 2 resistors and 2 capacitors. So if you already have those things around, and of course if you've got a scope around, which is probably the most kind of hardest thing to get access to in this whole setup for the hobbyist, if you've got access to those things, you can 100% do this already, probably today. Alright, so without further ado, let's actually dive into what the methodology for this actually is and how we can build this demo up from scratch ourselves. Okay, so for us to kind of understand what's actually going on in this XY mode, I've brought out another piece of equipment. This is a function generator or a signal generator, an arbitrary waveform generator, you might also hear it called. Basically, this is something that we can use to generate signals that we can plug in and sort of view on the oscilloscope or plug into other kinds of equipment. And in this case, what I want to do is to just give us some example waves up here that we can manipulate in a way and kind of see how they respond in XY mode. So what we've got here, you can see across these 2 channels, and these both go into these channels kind of respectively, is 2 sine waves, both at 100 Hz. The frequency doesn't matter, only that the frequency is the same in this case. And also you can see that these 2 waves are 90 degrees out of phase with each other. Or rather, we could say that in another way, which is one of these waves is a sine wave and one of them is a cosine wave. And if you remember back to trigonometry, what you actually know is that if you kind of plot out, the x position being the cosine function and the y position being the sine function, what you actually get is a circle, right? And if we go into XY mode, what we'll see is that we actually have a circle here. And this is kind of a really big hint as to how XY mode works, and it's kind of straightforward and obvious when you think about it, is that channel 1 is controlling kind of the x position, and channel 2 is controlling the y position. And as we sort of like take a snapshot of the wave and we plot all of the points where these 2 lines intersect, those give us coordinates to actually draw lines here. So that's how this thing works. I'll show you one more example of this for how we can get a little bit of an idea about it. So I'm going to change the wave again on both of these, and I'm going to set it up to be a ramp. And a ramp is basically, you might also know it as a sawtooth wave. It's basically just, going up diagonally. That's it. Or it could be going down diagonally, but in this case it's going up. And I'm actually going to change this so they're in phase with each other. And the idea here now is that we've got x and y doing exactly the same function, and they're both just going up. And what that's going to kind of result in is just a line that goes up. And this makes sense if you think about it, right? Because we're basically plotting the equation y equals x, right? And that is just a function that as you kind of go along in the x position, that corresponding x position is also your y position at any given point, right? And that should make total sense. So that's kind of a real simple and visual explanation as to what's going on in XY mode. And hopefully we'll make it kind of a bit more intuitive when we actually go over and we start doing things with a microcontroller and generating some signals through the microcontroller. We basically need to just make 2 signals which control x's and y's and do that in such a way that we get the effect that we're looking for. So without further ado, let's go into some more details on that side of things. Alright, so let's turn our attention to the firmware now. Everything I'm going to show you today is going to be built around this microcontroller and this development board. So this is an STM32F401RE, I believe. It's a Cortex-M4, but none of that really matters that much. You can kind of use any microcontroller you want for this, and you can sort of use any STM, and none of that stuff really matters, right? The architectural part is what's important here. If you do want to know exactly how to program this microcontroller and this development board, I have a whole series of videos about it. So go and look on this channel, on the playlists. It's called the Blinky to Bootloader. It's like 18 videos about everything from the first steps of getting this up and running with all open source tools and libraries, to actually getting all the way to writing a cryptographic bootloader for doing firmware updates, signed firmware updates. So that will really get you through some of the details if you're lacking that kind of stuff now. Anyway, let's turn our attention to the architecture diagram. So that's what I'm going to show you now. If we see here, this box, this contains all the firmware components. So the main thing that we've got are these two arrays. They're basically the points that we're going to draw to the oscilloscope. Basically the points of the thing we're trying to draw, the vector image. So it doesn't matter what the numbers here specifically are, but we've got a bunch of X's and we've got a bunch of Y's. And we need 2 pins of the microcontroller to output signals on. And we're actually just going to output digital signals on the microcontroller. So we don't have a digital to analog converter on this microcontroller, right? We have to generate digital signals and then somehow turn them into analog signals ourselves. And we're going to look at how we do that in a second. And basically, the idea is that we have 2 channels. These are our 2 pins, basically. And we're going to output PWM, pulse width modulation, which is basically a digital signal that has a fixed period of time. And we have basically a pulse every period, and we vary the length of that pulse in order to represent kind of different values. So we actually control those 2 PWM channels using timer 2 on the microcontroller. Of course, timer 2 is just a timer that happens to link up with these specific pins. The actual timer details don't matter that much. So in this case, I'm going to use timer 2 of this microcontroller. You know, this may vary for your purposes. Now we've got another timer that we use to actually just generate an interrupt at a fixed frequency. And every time we get this interrupt, we're going to go and sort of update which of these values we're trying to display using our digital pins. So we're just going to update the duty cycle. So you can imagine the first time we get this interrupt, we're going to grab the first 2 positions and we're going to display these 2 on channel 1 and channel 2 of the PWM. Set the duty cycles to these values. And then the next time we get the interrupt, we're going to show these next 2 values. And we're just going to set these duty cycles. And then again and again and again. And what we actually end up doing there is that we'll show a duty cycle of 39 for some fixed amount of time. And then we'll switch over and we'll show 102. And so we're sort of like really recording our points in time for a while so that they're there. And then the output of these 2 channels, which is the digital pins, right? So this is now going out of the board and out of the firmware. They go into 2 low-pass filters. Now, a low-pass filter is literally just a resistor and a capacitor connected together. Now, of course, that's not the only way to build a low-pass filter, but that's the simplest way to build a low-pass filter. An RC low-pass filter, resistor capacitor. And of course it matters which resistor and which capacitor we use, right? You can't just put any 2 together. They will always make a low pass filter, but we actually need to tune this to be filtering out specific frequencies, specific high frequencies, and leaving intact specific low frequencies that we're interested in. So we have 2 of these, 1 for each of the PWM channels, and these are where our 4 external components come from. This is it. This is the digital to analog converter. I guess together with the fact that this is PWM, this is our digital to analog converter. So it's very grassroots, and that's kind of why there are some artifacts around, and we'll talk about that in a minute. But basically the output of that then goes directly into the oscilloscope, and that's how we get our image. So let's just zoom out a bit and scroll down here. I've drawn a diagram which kind of shows this process of taking the PWM and putting it through these low pass filters. So what we have here is a PWM type signal where the duty cycle changes every period. Now in reality we don't actually change every period. We have some number of periods that go on where we show the same duty cycle, but just for the sake of illustration, this is kind of how this looks. So here what we have is the duty cycle, and the duty cycle is basically how long is this high compared to how long it's low, right? So this is high about 60% of the time and it's low for about 40%. So we'd say that the duty cycle is 60%. Now here it's around 20%, here it's around 40, and here it's around 80. Now this is what actually goes out. If we were to like look at these pins on the oscilloscope, we would see this square wave basically, or rather this rectangular PWM wave, very digital looking, right? It's either all the way high or all the way low. But we need it to show analog values here, right? We need this to actually show all the values between 0 and 3.3 volts, that this is the maximum voltage of this microcontroller. Because that's what we need to set. We need to have this nice continuous range of X and Y positions to actually get the oscilloscope to show something. So that is what the low pass filter is doing, right? It's taking out these high frequency changes, and by high frequency I mean the fact that this square wave goes from just being all the way here to all the way in the bottom, just in the blink of an eye, in the instant. That's actually what you would call really high frequency change. There's a lot of theory that goes into this kind of stuff, right? You know, understanding the Fourier transform and the fact that square waves are actually made up of like infinitely many sine waves of different frequencies, and that you have to add up a bunch of high frequency sine waves to get these nice clean square edges. Understanding that that's the actual nature of any signal that you're talking about. This is not just like one way of viewing it. It's really like every signal is actually composed of these fundamental building blocks. Then you understand that this actually contains a lot of high frequency components. So we need the low pass filter to sort of take that out and average over many periods to grab like actually kind of what we're encoding here, which is like 60% of our maximum voltage. So that's what the low pass filter does. It kind of filters that down to that level. And so this is kind of a rough, not quite accurate representation of how this would look once it's gone through the low pass filter. You can see that instead of having this nice changing, or rather not nice because we don't want it, this changing high-low value, instead we've got some fixed kind of, you know, stable 60% of the maximum voltage signal here. And then as we move to a 20% duty cycle, it slowly ramps down to that. Instead of being this sharp change, we take out those high frequencies and we slowly get down to that point, relatively slowly. And then when we go up to 40, we sort of slowly creep up. We don't instantly end up at that level, but rather we pass through intermediate values, and then eventually as we go to 80. So this is how we actually convert our digital 1 or 0 essentially into this nice continuous analog signal. And this is not a particularly good digital to analog converter. Like, there's a lot of loss in this. And actually, when you just have a single RC filter stage, that's not a very good filter, right? It still leaves in a lot of high frequency components. It doesn't really just take out everything. It sort of just turns the volume knob on those down a little bit. And sort of the higher the frequencies, the more it turns the knob down. But like, if you're kind of just around the point that you want to remove, you're still getting quite a lot of those. So this is not a good way of doing this, but it is a really simple way of doing it. So that's why it works so well in this instance, because we don't have to have more fancy components and more complexity in order to do this quite cool thing. But it wouldn't hurt your situation to have a proper dedicated digital to analog converter. And of course, some microcontrollers do, even from STM. Some microcontrollers have digital to analog converters built in. So if you want to make your life even easier than this, go and grab one that has a DAC. It will really help. All right, so the next big question is, how do we get to these points, right? How do we get to these X and Y values that actually sort of form the basis of the image we're trying to show? Well, is actually quite simple. You just sort of you draw yourself out a grid, you know, a nice plane, and you plot out the points that you want to draw, and then you sort of like list those points out in the order that you want to draw them. So let's say we start here at this point, 3, 3. Well, we want to draw a line between 3, 3 and 6, 3. So we sort of list those 2 points out one after the other. So we start here, we move to here, then we move up here, and we move up here and here and here, and sort of we try to move over all the edges of the cube, arriving back at the first point so that we've drawn all the edges. And then we do it all over again. And we take those coordinates, that big list of coordinates that we make here, right? You can just imagine there's a lot more coordinates, and eventually we kind of end up back at 3, 3 in the beginning. Or rather, you wouldn't actually record 3, 3, because then you would sort of be moving to that point twice. But you get the point. You list out all your coordinates here, and then those essentially, we need to do some processing on it, but essentially these components end up being your X and your Y positions here. So you just take the X part and you stuff it into the array, and you take the Y part and you stuff that into the Y array. That is basically how this works. Now we do need to do some processing on this, right? Because as you can see, this cube is sort of like hanging out here in space, right? It's not even like nicely stuck down here in the corner where you might, you know, only use a few values. Instead it's up here in space. But that doesn't matter so much, because we're actually going to process these points to normalize them so that we actually move that whole cube back down to this point, and then we're going to like scale it up to be, you know, in the range of values that our PWM can deal with. And we're going to talk a little bit more about that when we come to write the firmware in a second. But that's the basic idea. So let's imagine that we write down all of these points. How are we going to get those in? Well, that's what I'm going to show you next, and we're going to do that with a little script to just make our lives easier. So let's take a look at that now. All right, so now what we're looking at is a Python script, and this Python script is taking in these points that we just had. They're a little bit different to the ones I showed in the example video, because I drew them in a different way basically. But it is just a cube with each point kind of connecting to the next point, and each point is just an array of 2 values. And what we're actually going to do is just process these points into such a way that we end up coming out with like arrays that we plug in C. Basically, that's the idea. And there's just a couple of steps that we need to go through. So I mentioned it before, but essentially what we need to do is to take these points and normalize them, so that instead of, you know, being like 2, 7, it would instead be something like 0.01, 0.9 or something like that. Something that sort of like maps this like whole range of values that we have down into a small 0 to 1 range. So that's what happens in this point here. We kind of figure out what the extremities of our coordinates are, and they become our maximums, and then we sort of divide everything down by that. So we normalize, and we then scale the points back up to our maximum scale, which is, you know, 256 minus 1. 255 is the highest number that we can represent, so we scale everything up by 255, and we then extract out the 2 arrays as just 2 lists, right? So we loop through, we grab the first one, and what I'm doing is these are actually floating point numbers now. What I'm doing is I'm turning it back into an integer by adding a half and then casting it back to an integer, and that is basically, the adding a half is just to try to make the rounding work correctly. So that's what we end up doing there. Okay, and that's pretty much it, because that will give us our 2 lines. There is one more step, and this step is maybe not obvious until you actually go to the real hardware and you start doing it, but actually just having a single point and then jumping to your next point is not the best way of doing it. Because it's actually better to interpolate between each of these points a little bit, so that instead of going immediately from 2,7 to 5,7, you sort of do a few of the intermediate steps between 2,7 and 5,7. You interpolate some points between that point. And the reason that we do that is because like in reality, when we put this through the low pass filter, when the oscilloscope is sampling and everything like that, you won't get this nice clean line drawing across. Instead, you'll get something kind of a bit smushy and a bit more smushed out by the low pass filter. So instead, we explicitly kind of put in some of those in-between states in a really linear way, and that kind of removes some of the noise that we have from the whole process and from the low pass filter and from everything else in the chain. I found that this really helps, and you need to basically make a trade-off between like how much interpolation you do using this method, because interpolating scales your signal out, right? So if we say here we're going to do 7 points of interpolation, that means we're adding 7 extra points to this whole thing. So if we had, for example, how many lines do we have here? We've got 18 points. Well, then we have to multiply the actual number of points that we have by 7. So 18 times 7 is the number of points that we have to show for a single frame. So as you scale that up, if you start thinking about the sort of frames per second that you actually want to show something at, then the more points you add, the more stuff you have to do in a single frame time, and the faster everything has to be. And as you increase the frequency, the speed in which you change things, you actually have to start being much more detailed about how you're filtering, because you're putting in much higher frequency signals and you want to maintain this low frequency signal. So it becomes a little bit tricky to kind of balance all of that out. This is kind of a good place that I found to do this. So this is what we're going to be working with in the beginning. So let's actually take a little look at this first. I just want to actually plot some of this stuff out. So I'm just going to plot the signal here. So I'm just going to take x's and plot it out. Let me run the script. I hope it works because I haven't run this part for a little while. So this is going to be Python interpolate points. So we run this, and this is kind of what the exposition signal looks like, right? We start down here, we do a bunch of points in the middle, and then we get to here, we go up to the top, and yeah, this is what this signal looks like. And if we just like scale this out a little bit, so instead of just showing one iteration of it, we show, say, 3 iterations of it. You can see that this is what we would expect to see on the oscilloscope as a represented signal. Now, something to note here is that this actually still has a lot of high frequency components. We're still moving from this point to this point really quickly. We're still dropping all the way down here. So it's not quite enough to think of filtering out just to really like pure sine waves. You need to filter out all of your switching and the PWM switching noise, but still keep in enough frequency so that you have this. So that means you need to slow this down quite a lot in order to remove the high frequency stuff and still keep these nice sharp edges. So there's even more of a trade-off you have to make there. You have to try and keep things slow as possible, at least in this setup, right? Using this kind of digital to analog conversion method, you can't go that fast. So that's one trade-off. This is what the exposition looks like. If we look at the Y's, they look fairly similar, to be honest. Like it's a different signal, but they look fairly similar. You can see that it's still kind of spiky and jumps around. And of course this makes sense, right? Because we're actually just trying to represent points of a cube. We're actually going to be kind of just moving between these kind of fixed values, one after the other. Okay, so then, and of course there are a bunch of functions up here for doing these things that I've mentioned. So the lerping and the interpolation and the oversampling and all of that kind of stuff. And then what I've done is to write just a couple of small functions here that will allow us to dump out this whole thing as like nice C arrays. So if we run this now, you can see that this dumps out in C. So it will tell us like, here are the number of points we have, 126, after kind of all of the scaling and the interpolation. And here is a uint8 array of all of the values. And these are just some simple Python stuff. to actually generate this this text. So this is what we would go and paste into the firmware. Right, now what we're going to do is we're actually going to write the firmware. So we're going to set up the timers, we're going to build all of this, and we're going to see this thing work with a static image. So that's the next step, and then we're going to get to the animation after that. Okay, so now here we are in VS Code, and I have basically a kind of template firmware ready to go, and we're going to build this out, and this is going to kind of be where we write all of the main code that we just looked at in the architecture diagram. Now, this is like a basic skeleton from using the libopencm3 library, which is a kind of low-level hardware abstraction library for a lot of different ARM cortex-m4 and m3 microcontrollers. It's kind of great because it gives you kind of nice uniform ways of accessing things like GPIO and timers and PWM and all of that kind of stuff without having to force you to get into all of the details of every specific microcontroller. And since we're trying to do something general here, I'm actually more in favor of that anyway. Even though we are going to have to look into some of the details of this microcontroller in order to set it up correctly. Now, what you can also see is that, oh, and by the way, of course, if you want to get more information about this, again, I made a whole series about the bare metal programming of these chips, and I go into a lot of detail about how libopencm3 works. I dive into how all of the functions inside it work and what they actually do at the register level for this chip. And so you'll see how all of this works at a kind of a deeper level if you go and check that out. Now we're going to use it more as a tool, and we're not going to go into too many of the details about it specifically. All right, but what we've got here is a couple of libraries loaded up from libopencm3, or a couple of header files rather. We've got the core system that just sets up the clock frequency for this chip. We're running at 84 megahertz. That's not that important, but just so you know. Then I've set down some defines here which are related to the specific kind of like wiring up a single pin to a PWM. And I'm going to show you where I got these values from as well, so that you're not thinking like, well, okay, but where did these come from, you know? This is just a magic value here now. Then we have some empty functions. I'm going to fill these out with our implementation, and this is basically going to be how we set up the timers and how we set up the GPIO. And then what you can see here is that the main function that gets, you know, kind of like this is the main firmware that runs, like there's an infinite while loop with a return 0. I'm never going to get to that 0, but we just call these functions here, you know, the setup for the system, for the core clock and the GPIO and the timer. And the idea is that actually this main function isn't going to do anything. Everything is going to be driven based on the interrupt that we end up writing for this microcontroller. All right, so let's kind of just get into it now. First of all, I want to show you where I actually got these things from. So for that, we actually need to make our way over to the datasheet, and I've got that here for you. So this is the datasheet for the STM32F401 type series, and you can see the datasheet contains like all of the high level information about this chip, all of like the measurements and the like exact like pin layouts and all the stuff you need like mechanically and electrically, and all of the like big understandings that you would need if you're going to throw this chip into something and use it in a product. Like all the various disciplines would need to like read the same document and figure out, is it going to work for our purpose? The main thing that it has for us is the pinouts, and of course this shows you mechanically the pinouts and like electrically and all of that kind of stuff. There's also a big table down here called the alternate function mapping table. This basically tells us how we can take all these general pins of the CPU and turn them into specific functions. And the cool thing about these chips is that, they don't just have fixed functions on each pin. You can sort of say, well, this pin in this case is going to be a timer, and this pin on this case is going to be UART, and this pin is going to be SPI. Right? You can mix and match those and move them across different pins on the chip. Of course, there are actually only a limited number of things you can do on those pins at any given time, but it does give you some options on how you end up setting that up. The only thing we really care about in this instance is finding a bunch of pins that relate to a single timer that give us access to a couple of channels, and then that will give us the freedom to choose whatever other timer that we have in order to actually generate the interrupt. We need 2 timers, remember. Okay, so basically what I've done is I've just chosen 2 pins basically at random, or rather as the easiest convenience for me setting this up on the board. I've just chosen pins PA and PA2 and PA3. And what we can see here is that they are related to timer 2, channels 3 and 4, right? And they correspond to the alternate function 1 on the chip. So this information, that's what I've got down here in this like block of defines here, right? The port that we got for PWM is GPIO A. We're using port A, and we got pin 2 and pin 3 as our 2 channels. And finally, related to the PWM output channel, we've got those 2 linked up here as well, because it's output channel 3 and output channel 4. So that's kind of like all of the setup that we have for those pin values, right? And you can just sort of change these values to match whatever other system you use. I'm not going to make this completely generic. You'll have to go in and tweak it if you end up doing it in a slightly different way. But let's actually go now and set up the GPIOs. First thing we need to do is to enable the clock. Always want to enable the clock as the first thing you do with the peripheral. Otherwise, it won't work and you won't have any idea why it's not working. It's usually that you forgot to enable the clock. Can you tell that I've had this happen a couple of times? So peripheral clock enable, this is a function that we call. We just pass which clock we're trying to enable, and in our case it's GPIO A, right? We want to turn on port GPIO port A. Then we want to call GPIO mode setup, and we're basically just like kind of configuring some pins here now. So we're going to set up for the GPIO PWM port. We want to set a couple of pins up here in the alternate function mode. That's all we're doing here. We want to say that we don't want any pull-ups or pull-downs. So pull-up, pull-down, none is the option we're going to choose here. And finally, the pins we're actually using are PWM channel 1 and PWM channel 2. We can actually set those up in one fell swoop using this bitwise operation here. Okay, and next what we're going to do is we're going to set up GPIO set the alternate function. Now we'll take out this middle option. Here is where we're going to write which alternate function we have, and is, as we know, alternate function 1. That's all the setup that we need for the GPIOs. We've basically told them now you're in a timer mode, you're in PWM mode, and that's going to be your job. You're going to be the output channel, or the output channel of this timer. So that's what we've done here. Okay, and now in the timer setup, we need to kind of basically set up our 2 timers. One that's going to deal with the PWM on these pins, and one that's going to deal with like just giving us an interrupt at a fixed interval. All right, so again, first thing we want to do, enable the clock. Excuse me. Rather than it being the GPIO, this is going to be timer 2. Remember, this is the timer that I've linked up with these pins, so that's the one we're going to use. And now we need to call a few functions, and I've got some notes in front of me because it's easy to forget one of these functions, and if you forget to call it, or you basically forget to set up the timer in a certain way, it just won't work. So I've got the notes in front of me, and I'm going to basically go through them. So first thing we want to do is to set the mode. This basically is, just a really high level setup of the thing. It tells us like what kind of clock division we're using, and we need to just paste in various values that it's going to be looking for. We're not going to go too much into detail about what all of these different things mean, like the alignment and all of that kind of stuff. CMS edge Tim CR1 direction up. So this is just like high level setup for the timer, you know, like how do we divide the clock down? Where do we align on kind of edges or in the center? It's like that kind of thing is not that important for our purpose. And kind of how are we counting? Are we counting up or are we counting down? Because you can do both. In our case, we want to count up. So when we set up the general stuff for this timer, now we want to set up the output channel. So we want to set out the output channel mode. So this is going to be timer 2. And which output channel? Well, we're going to set up these two output channels here. So this is going to be PWM output channel 1. And then we choose the mode. And the mode, of course, is PWM. And it's the PWM 1 mode. And you can see what these different modes and all of these different options are. You can see that in the data sheet, the reference manual for this chip. So yeah, that's where you can find that information. We need to set this up for both of these, so they're both setting up these output channels as PWM. Now that we have that, we want to actually set up the frequency of the PWM that's going to be running at. And the way in which you work this out is you split it up into two pieces, right? You've got something called the prescaler, which is like how much the clock gets divided by like the incoming clock for the timer, how much that's divided down by. And you have something called the period, and that's essentially how many divisions you have in your duty cycle, like how many little increments do you individually have. So that gives you the ability to have like fine-grained, and we want 256 fine-grained increments in our PWM. So that's how we're going to set it up. And there's actually an equation that tells us what the frequency is of the PWM. So the frequency is the clock frequency of the chip divided by the prescaler, so that's the value of the clock division, multiplied by the period. And in both these cases, these are actually -1 because you would never specify a 0 value, so you don't waste the space. But basically, this is how we work out our clock frequency. So if we know what frequency we want on the output here, and we know what clock frequency our thing is running at, then we can kind of work out like what this multiplication could be, and then we can work out how we're going to divide it up. So let's actually just go over to Python for a second, and we can compute what we want this frequency to be. So I'm just going to tell you that I want the frequency of the PWM to be about 26 kilohertz, let's say, like 25, 26 kilohertz. So that's 25 or 26,000 times per second that we are getting a PWM period. Okay, so in order for us to do that, let's say we take our clock frequency, which is 84 megahertz, and we divide it by, say, 20. What did I think I set this actually up as 25.6 kilohertz, so 25,600. And that gives us this value here. So we need to kind of split this up. And if we take this value here and we divide this by 256, that gives us around about 13 on the thing. And this is kind of rough. We don't have this exactly split up, but basically I'm going to take this to be the prescaler, and I'm going to round it up to 13, and then we're going to have 256 levels, and that will give us about 25.6 kilohertz. Again, it doesn't need to be exact. I just want to have something that's quite high up in the frequency range that we can filter out, that's not going to be related to all the range of frequencies that we're trying to keep. Okay, so timer set prescaler. For timer 2, the prescaler is going to be 13. So rather 13 minus 1, because you always have to minus 1. And then we want to set the period, and we want to set the period as 256 minus 1. Okay, and that gives us our 25 kilohertz. So let's say 25.6 kilohertz approximately is approximately equal. Okay, so now we've set that up. The last thing to do is to actually enable the counter and the output channels. So we want to do timer enable counter. I can't type. We want to enable the counter for this timer, and then we want to enable our output channels. Output. And that's going to be PWM channel 1 output compare, or output channel PWM 2. Alright, so that is all the setup that we have for the PWM. And now we're going to actually set up the timer, set up the interrupt. Okay, so for that, we want to enable timer 3, because we're just going to use timer 3. We want to set the exact same mode up for timer 3, just counting up, no regular divisions, just keep everything simple. Then we also want to set up an output compare mode. And this time, instead of doing PWM, we're going to do something called active, which is basically just like when we reach the end of the duty cycle, so to speak, or when we reach the end of our kind of counter period, we want to get an interrupt. And that's what output compare active is going to give us. So now we're going to set up the prescaler and the period. And this is kind of less important in a way. Or not less important, but we don't quite have to think about the period and the prescaler so much. We could just think about the frequency we want to run at. So in order to do this, we can say that I'm just going to tell you that actually I want to run at about 750 Hertz. This is the amount of time that we will run, and like how often we're going to change which point we're kind of outputting on the duty cycle. So like which analog point are we showing at any given moment? And I want that to be about 750 times per second. So in order for us to get to that, again, we need to take our 84 million and divide it by 750. That gives us this number, which is 112. And yeah, we can just sort of divide this down, right? So it doesn't really matter. If we say divide this by 1,000, that gives us 112 on this side and 1,000 on this side. So yeah, that's enough for us, right? Prescaler of 1,000 and a period of 112. And that will give us our 750 Hertz. And again, it doesn't matter how we divide those two because we're actually just going to get the interrupt at this fixed frequency. Okay, last thing for us to do on this side is again to enable the counter. So we want to enable the counter for timer 3. Both of these should be, in all of these cases that I've left it as timer 2, this should be timer 3. That would be fun to debug. And I think then we need to enable the timer enable interrupt. What is the... How do we get the IRQ? Enable the IRQ, so that's going to be TIM3. And which IRQ do we want? And in this case, what we want is timer IRQ. How do we specify this again? No. OCM. OCM. No, I'm thinking about this wrong. Which one? We want to get a timer IRQ. Okay, what do we end up plugging into this? I didn't write this down, so this is great. So it's the DIER. DIER. Oh yeah, so we want to have actually the CC1. Where do we specify this? The CC1 interrupt enable. That's what we want. So channel 1 here is our interrupt. So basically we want to get an interrupt for channel 1. Because we're just doing channel 1 here on this whole thing. I guess we also need to make sure that we timer enable. I guess all of the channels are running on this. We'll check that anyway. But so we're going to set this up, and then finally we actually need to enable the interrupt via the NVIC, the nested vector interrupt controller. So we want to enable this, and that's going to be NVIC timer 3 IRQ. That is all of the timer setup that we need to do here. And then finally what we want to have is the interrupt handler being called. So I'm just going to set that up now. That's just TIM3 ISR. So basically this function is sort of defined and set up in the vector table by libopencm3 for us. We just need to implement this function. So that's what I'm going to do here. And the main thing that we need to do inside this timer, in fact, is to just make sure that we clear the interrupt so that whenever the interrupt occurs, we shut it down. So I'm just going to do that quickly before we even get started. So we're just going to clear the flag for timer 3, and the flag is going to be the TIM, and this one is the SRCC1 interrupt flag. So whenever we get this interrupt, the CC1 interrupt flag, we're just going to get rid of it. So that's the only interrupt we have enabled, and we're just going to make sure that it turns off and we don't immediately get it again. Okay, what I'm going to do now is I'm just going to make sure this compiles, and I'm going to actually run the firmware and make sure that we're getting this interrupt. So before I do that, I'm just going to disable the interrupt so we wouldn't get it. So I'll make, okay, that seems to work. I have the board connected, by the way, so that's how that works. I've got a breakpoint in the ISR, and it's not running. And that makes sense because I just disabled the IRQ. I'm going to now enable the IRQ. We'll recompile, set it up again, and now we're getting that interrupt. And of course, we're getting it way faster than I can like show with a breakpoint. So that seems to be working great. Okay, all right. Now what we need is to take those values that we generated in Python and actually put them into our program. So that's going to be running the interpolate point script, which gives us this output, and I can just throw that onto the clipboard with my clipboard command, which I find very useful, and that is going to give us our C code here. All right, and then let's just trim off those the spaces. So we've got 126 points, and yeah, we're going to run through here and basically change the duty cycle each time. So let's make a UN8T point index. It's going to start off at 0, and what we're essentially going to do is to just every time we get this interrupt, we are going to like set the X and the Y channel duty cycles up to this point. So timer set OC value for timer 2, and that's going to be PWM output channel 1, and the actual value that we want is going to be X's at point index. Same thing for channel 2, except we use the Y array. And then we're going to take our point index and we're going to say that it equals point index plus 1 modulo the number of points that we have. And that's going to just cycle it back around. And now the next thing to do is to actually check and see if this works. So what we should see effectively is some PWM, and we're not going to really be able to get a good sense of that right now, but once we hook up the filter, then we will. If we see good PWM and changing frequencies and stuff, that's great. All right, so I'm just going to run it and flash to the board, and then we'll take a look on the scope at how this actually looks. Okay, so we're looking at the scope now, and I've got it hooked up with the two output pins. And what we can see is that we do indeed have PWM on both of these outputs. So you can see this is channel 1 here, and this is channel 2. What I'm going to do is I'm going to zoom in. I'm going to kind of check to see if this kind of makes some sense, because right now you can see it's just changing, and there's not really a lot we can really decipher out of it. So I'm going to just zoom in, and I'm going to take a single trigger on. I guess we're triggering on channel 2 right now. So let's zoom out a little bit. Run another one. Zoom out a little bit more. So what we can do is we can now measure from one point to another, and it's quite interesting that these two are a little bit out of phase with each other, but I'm not sure if that's something I'm doing. I'm just going to take another single. Take a few single steps here. I think what we can do is we can take the rising edge here and just compare it to a previous rising edge, and that should give us, oh sorry, that's a falling edge. So just find a place where we can get to see a couple of rising edges, and then we can take a measurement. So I'm going to take a measurement now. I'm going to go to the cursors, and we're going to stick one on this rising edge here, and then I'm going to select this cursor. I'm going to move it over to this rising edge here, and we can see that we have a frequency here. It's a little bit blurry on the screen, but it says 25.51 kilohertz, and that is actually what we would expect here. So I think, at least from the terms of setting up PWM and having it output, this looks kind of correct now. And if we just kind of let it run, you can see that there are definitely a lot of different kind of values that are going on, and there is a definite repeated period here that we can see. So there's a bunch of stuff that changes in the middle, but then there are these kind of dead spots in the middle. So that kind of shows that there is some periodicity going on in this image. Let's see if we can make a filter up and see if it will actually work, and we can get the analog value out. Right, let's try that. Okay, so we're going to build our filter up on, or our filters rather, we need two of them. We're going to build it out on a little breadboard. And of course you could use a piece of perf board, or you could, design a PCB if you were so inclined. You could do all of these things. I'm just going to do it on the breadboard for now because it will be a little bit simpler. So basically, if you remember from the architecture diagram, I showed kind of what a low pass filter looks like, and it's kind of something like this. Basically, our input signal comes in, it passes through a resistor. That resistor is then connected through a capacitor to ground, and we take the output from the node between the connection of the resistor and the capacitor, and that's our filtered output. So that's just how this thing works, and kind of actually, if you think through what that kind of means in terms of like the physics and like, what effect this would have on an incoming signal, it kind of makes sense. You're charging the capacitor sort of will discharge at different levels, and so like it will sort of charge up and discharge, and that will affect the voltage that you see at this point. And kind of if you map out the right ranges here, you'll get to it. So that's the idea. That's what we're going to put down. So I'll just put that kind of here next to us for a reference. But yeah, so like, which values do you actually pick? Well, what you need to do is you need to actually calculate what kind of frequencies you want to let through. And if you think about what we just did in the firmware, we set it up so that every 750, or rather 750 times per second, so 750 hertz, we change our position, right? We change the duty cycle. We go to a new point. And we don't want to pick up like kind of all of that noise of that whole it's not that we need to pick up that frequency in order to display this image. So what I've done, and I've actually done it through experimentation, and I'll tell you how I did that in a minute. But basically I started with a ballpark and I got through experimentation these values. We're going to use a 1 microfarad capacitor, and we're going to use a 648 ohm resistor. Now that's not a standard value, and I've actually soldered kind of two resistors in series in order to get this value. So it's kind of cheating. I said it was 2 components, but really I guess this is 3. I mean, I guess you'll forgive me and tell me this isn't clickbait, but I just didn't have this kind of resistor value in my own stock, so I kind of made this one up together. But I think you can find something in that range. What this will do is this will create a filter of around 250 hertz. Now, it won't cut everything off above 250 hertz. It just starts to attenuate it, right? It starts to dampen those signals off. So that will leave us something. It will also leave some noise in, but this will give us something that is keeps enough of the original wave and lets us, you know, get to the essence of that spinning cube. So let's actually build this on the board now. So the way I'm going to do it is we're going to come into this. We're going to come in on two sides, right? We're going to come in over here, and our signal will come over here somewhere. And then we're just going to build a kind of symmetrical circuit on two sides. So I'll put that over here as well. So input's going to come in here. We're going to pass through the resistor, the one resistor we kind of think of it as, but it's two. And then we're going to go into the capacitor, and these capacitors are polarized, so this is the negative side. So we're going to go through the capacitor, and like the capacitor is going to go to this middle point, that's negative, that's going to be ground. On the other side, then we need to kind of go through that and kind of into the same point, so they end up sort of sitting next to each other. So this point is ground, and what I'm going to do is I'm just going to stick a little wire in here because we're going to need to connect the ground clip of the scope, and so I'll just put that in there, and I guess I didn't really need to go through a small wire. This will give me somewhere to connect the ground clip to that's out of the way. And then what I'm going to do to be able to take the signal, so the signal actually comes out at this point and at this point, right? These are where the resistor and the capacitor meet, is these points. So I'm going to stick just a little pin header in there at this point, and then we can clip the scope to these points. All right, that's it. That's the filter built. Yeah, it looks exactly like the schematic, and now we can pump in our PWM and observe the signals here. Oh, and one last thing, just to emphasize how I actually got to this. I started out with a capacitor value of around 1 microfarad, right? I just figured that that's a good place to start. And then since this, you kind of get to this filter through a multiplication of the resistor and the capacitor together, where you can just vary the resistor until you find the right filter value. And so what I did was I just wired up a potentiometer as a variable resistor, and I just sort of found the right point using this. And I also validated that with the calculations that I'd done to make sure it was kind of sensible and the calculations also made sense. But this is a pretty good way of tuning in to exactly where that filter makes sense. And of course, the more number of points you have and the more the different frequencies you choose, you'll have to tune these filters anyway. So this is a good way to just, you know, find your way to the right point. Anyway, let's give let's wire this up and give it a shot. So I'll just slide into frame here the development board. I'm going to unplug it for a second. This is the development board, and over here on these two pins we actually have the two PWM channels. So I've got these on a white cable and a brown cable, and they're just going to go into our 2 points. So let's just wire those up, and I realize this is not great framing here. So we're going to come into this point, and we're going to come into this point, right? Our two filters. So this is channel 1 and this is channel 2. And then we need a ground point. So this is ground, and what I will do is I'll just take this this ground wire and plug it in between these two capacitors there. So that's the final filter, and now we can just clip onto this and view these 2 points here with the scope, and hopefully that will work. So let's get that set up. And this is what it looks like on the scope. So yeah, that actually looks like that's worked really well. Just for some context, I want to go back and show you what our kind of plotted signal looked like, and this is going to be the plot for channel 1. So this is what channel 1 kind of should look like. So we've got these two cat ears that come down into a little spike, and this sort of flat thing here, and then we repeat that. Well, let's go back to the scope. Yeah, we can totally see that. Two cat ears into a little spike, sort of jump up, a little flat edge here. That actually looks really good. So the next thing we need to do now is we need to get this actually set up in such a way that we filled the screen on the scope with the image that we're going to be displaying. So let's do that quickly. Let's just get this signal dialed in. In order to do that, I'm going to start on channel 1 and bring the position all the way down and just scale the thing up. Now that's too much, but we can go into a fine adjustment mode and bring down those peaks until they just sort of fill the screen. And I think we're a little bit off on the bottom. Something like that. And then let's bring those edges down at the top as well. And now we're filling the screen nicely. So that's 242. And my bottom edge is, oh no, so around minus 2.3. And then we need to bring that top edge down to about 254. Do the same on channel 2. We'll scale it up and bring it down. And so about the same bottom level, and then we'll fine adjust until those peaks fill the screen and we're not clipping out. Okay, and now we're going to go into XY mode and see if this actually worked. I really hope it did. Alright, look at that. We got a cube. It's a little bit out of, you can see that it kind of goes out the screen, so that means that we are not quite with the right vertical level, but let's kind of just try and adjust things up. Oh yeah, I see it was out of, it was kind of beyond that point. Let's try that again. Looking a bit better. Let's go back to channel 1, maybe we're clipping off there. Oh, that was not great. Scale the whole thing up until hopefully we're just inside there. Alright, that's it. That's the cube image. Now, of course, this doesn't doesn't really look incredible. You can see it's quite janky at this edge here, you know, kind of when this corner comes up to meet this corner, and you can see there's a bit of jank here. These corners don't really match up. This corner is also kind of messed up. And I think what's happening there is actually that during the normalization and then the scaling up process, and then the truncation from a floating point number to an int, we're kind of losing quite a bit of resolution. And that combined with the the fact that we only actually have 256 distinct voltage levels, is kind of meaning that we're, you know, instead of coming up to this next point and rounding up to be here, we're sort of rounding up to the last point, and then we're already jumping over here before where we should be jumping from here. And I think that's the main problem. So, and definitely, of course, the actual analog conversion that we're doing here using the filter is also not ideal. And there's a bunch of noise here. But in general, it's pretty good for what it is. This is the principle. We've drawn a cube. We can definitely get this looking better. I think if we were to add more interpolation points, this would look a lot better. But now that we know the general idea and we've proved the concept, we've built the filter, we've built all the firmware, I want to show you, and we won't build it from scratch, but I want to show you the cube animation code and kind of give you a quick walkthrough of it. Because it's not that complicated, and it's basically just an extension of this exact principle. So let's take a look at that. Alright, so this is going to be the final step. How do we go from that kind of static cube drawing that we just saw into the nice kind of, well, kind of low resolution, but nice rotating 3D cube image that we saw in the very beginning? Well, yeah, of course we actually don't need to go through such a manual process of scribbling down all the points and figuring out the actual like coordinates of those points and then doing all of these transformations on them. Of course we can do all of that in code, right? So basically, essentially what we're doing here is to write a tiny little 3D renderer on the microcontroller itself and actually kind of figure out all the computations and the 3D math that we need to do in order to spin a cube around and just end up showing that on the output directly. So that's what I'm going to show you now. And the way, and that's basically what we got in this code. Before we actually go into the code, in fact, what I'm going to show you is how I got to this, because I don't just know how to rotate a cube from the top of my head. Although I know some people do, they could just write this in in an instant. What I did was I went over to this website, Rosetta Code. Well, I actually Googled for 3D rotating cube code, and I got brought to this Rosetta Code, which shows a whole bunch of different languages and how you can rotate a cube and display it. And yeah, it's actually a really interesting resource if you want to kind of figure out how different programming languages work. It will give you some of this stuff. I ended up going for the JavaScript implementation just because it ended up being the one that was the most direct and not trying to use any libraries or anything. And of course, like trying to port this to a microcontroller, I don't want to have any libraries involved. I don't have any special math things. So all the ones that were involved with Python were either using things like NumPy, or they were using like special rendering libraries. Even the C code was doing some special stuff. So I ended up going with the JavaScript one. And it was kind of a good choice in my opinion. So what I did was I downloaded this code, and let me just show you it running kind of in the browser here. So this is that JavaScript code, literally almost directly copy pasted and shown here. I've made a couple of adjustments to it, but you can see like this is exactly what I was going for. It definitely looks cleaner in the web browser than it did on the scope, but yeah, this is the general idea. So I basically grabbed that code, made some changes to it so that it actually drew it in the way that the scope would draw it. So that is like go from one point, draw to the next, overlapping previous edges, because I needed it to work in basically exactly the same way that the scope would draw this. So I ended up refactoring this a bit. So it's not exactly this code, but it's pretty close. I took most of it. And now let's go and look at the ported C code. And I love the irony here, because I think it's kind of funny. I think a lot of people don't expect that you start out with JavaScript code and you port it over to C, to get this, this like, this like low level thing running. But yeah, this was the way I did it in this example, and it turns out to be the most useful way. Okay, so the basic setup's the same. We've got these things. We brought in the math library, so we needed to link that in. That's something you need to do. Same PWM setup. What I have now is a structure for a point in 3D space, vec3. Just holds floating points for x, y, and z. Have a couple of constants here, so we've got pi, floating point number in pi here. We've got the number of interpolation points that we're using. So like that's between drawing a line, we draw, say, 8 individual lines instead of drawing one big line. Sorry, I hit the microphone there. The number of points we have in a cube is just 8. That is just the number of points that we have. This is a cube. So this is a completely, like, these are the points of a cube. You can see they're specified here in a normalized way from minus 0.5 up to 0.5. It's not completely normalized, but it is still of a range of 0 to a range of 1. So we can quite easily modify this. And then these are just some extra things. So these are the edges, or rather the edge indices. So basically what this says is that we're first going to start at this point 0, or the 0th index in this cube. And then we're going to draw the first index, and then we're going to go to the third index. And we sort of do it like this. So we sort of go back and forward between drawing between these different points based on these indices. And this isn't that different to what we were doing by hand in the sketch. So if I go back to this sketch and I open up the basic image, like what we were doing essentially was saying, okay, we start at this point and then we're going to this point, right? And then we're going up to this point. And now kind of what we've done is we've named all of these points. We've given them an index, and we're just saying, well, go from index 0 to index 1. We've taken out some of the manual part of figuring out, these points. And now we've taken it up one level of abstraction, and we're saying, draw index 0 of the cube to index 1. And that's kind of the idea there. So these are all the edges. And of course, this actually does cover the fact that we need to go back over our previous edges. And that's something the original code doesn't do, right? It just draws this edge to this edge to this edge, this edge, this edge, this edge, because we don't need to actually, when you're drawing on the computer, you don't actually need to go over your previous edges. Okay, so basically, what we're going to be doing at any given point is drawing, just setting our duty cycle to some value. That's what we're doing. And we have to compute all of these in-between points. So we need to compute all the points between two edges, and we need to do that with this linear interpolation, and we're going to have 8 steps of linear interpolation. And at any given point, we're going to be drawing, something between these two vectors here. So that's why they're set up there. There is a function to rotate the cube. So what this does is it mutates the points inside this cube using a rotation matrix, essentially. It only rotates on the X and the Y axes. It doesn't rotate on the Z axis. You could do it and it would be exactly the same. You just have to do a little bit more math. This basically is just the rotation matrix of a cube, or a rotation matrix in 3D space. Yeah, it's not too complicated. If you need to study a little bit of linear algebra to figure out like how these things work, how the rotations work, but you can see we're using sine waves and cosine waves. We're just rotating things, right? We're using angles and waves to do this. So that's how that works. You can look deeper into that. There are plenty of videos about that. Then there's a function that does translating and scaling. So basically takes our points, which are in this this kind of normalized tiny 0.5 to 5 0.5 space, and kind of offsets them and scales them back up. And so we offset by 1 and we scale back up by some amount. And it's kind of a bit of a weird set of constants that are around here, but this is what I used to make it work in the end. Here's a lerp function, linearly interpolate from A to B over this value from 0 to 1. So, how much of A do you have and how much of B do you have? Well, that's determined by this equation. Here's the ISR, the interrupt service routine for the timer. Basically, what we end up doing is figuring out our X and our Y values, right, our duty cycles, based on taking these two vectors that we have, these two 3D points, and just drawing the X and the Y positions of these 3D points. And this is why this isn't a true 3D, or rather a perspective 3D rendering, because we don't actually, points that are further away don't appear to be smaller. So there's no perspective in this. They're literally, a point that's further away will be drawn sort of the same size, so to speak, as a point that's close to you. So this is more of an orthographic projection rather than a perspective projection, which involves more math. Basically, you need to actually do additional math to then project the points that you have into this scaling space. But that's an exercise for the reader, or the watcher in this case. So basically we take the X and the Y points and we just render those. So there is a Z point that's being used, and it's used in all the calculations, but we don't actually use that as the point to draw on the screen. We only use the X and the Y. But that's actually enough to get this nice flat screen image of what we're looking for. That actually works. So we end up interpolating between, and we use this lerp index, and we basically go from 0 to 1, so over 8 steps. I just pre-computed these values because I thought it would improve performance. I don't think it actually matters at all, because the actual limiting factor of what we're doing here is the 750 Hertz update rate, which in terms of the math for what we're doing is we can do that math really quickly. So we don't need to worry too much about that. But I did pre-compute the points here. So basically we do that. We then do a modular increment on the lerp index, which is a fancy way of saying we take the lerp index and we add 1 to it, and then we modulo over the maximum. So I just put this in a macro because we use it in multiple different places, and it's kind of nice to just sort of explicitly put it out there. Could also make it a function. So what we end up doing is computing those points, setting the duty cycles, And then we sort of just need to go through a process of figuring out like what's our next point. So if we're still interpolating between values, then we just continue interpolating until we got to the end, right? And since we do a modular arithmetic here, if we end up at 0, that means we've interpolated all the points between 1 and 2. So we need to then increment the edge index. And then when we increment the edge index, basically we're checking to see, like, at any given point we're drawing 2 edges, right? Or we're drawing an edge. So, like, first we're drawing all the points between here and here. So we draw, linearly interpolate this point to this point. Then we're drawing from here to here. So then we're linearly interpolating every point. Eventually we come back around and we get back to the very first point. So then we need to start the whole thing again. So that's what this statement is basically checking. Like, have we drawn all the points? If we have, essentially if we're at the beginning of this whole operation, then what we do is we do a rotation of the cube. So we rotate all the points of the cube by some small angle, and then we figure out the next points for V1 and V2. So this is the edge essentially. So we take the first point in the edge and the second point in the edge. We do all the translation and the scaling to get up into the actual range of values we're interested in, and then that's it. We just continue because that's what we're going to use here on the next round. If it's not the last point, right? If we're not done, then what we actually in fact do is to just reassign the previous edge that we had on V2 and set that to be V1. Because remember, again, you're always going to go from this point to this point, and then this point to this point, and then this point to this point. So sort of like this point is involved in first this edge and this edge. So we actually don't need to go and recompute this whole thing. We can just say, well, okay, this is V1 now and V2 is this next one. So that's what's happening there. And that's the whole logic of it, right? All of the timer setup stuff is the same. All of the GPIO stuff is the same. The only difference here is that we kind of set up the initial rotation of the cube before we actually start the timer, and we figure out the first 2 points, and then that's just the way I set this up. So that is how that works. I hope that's enough detail and you don't mind that we didn't write this together on camera, because it would have just been a little bit of a nightmare to try and remember how to do all of this without making mistakes. That's pretty much it. I'm going to leave you with one final look at the cube, and yeah, let's see the final result. And that's it. That's the 3D cube rotating in all of its glory. This has been a real fun project. It's been a real sort of journey to go on in order to get this all to work. And I went through some different iterations and some different kind of dead ends in order to try and get this to work in the way that I wanted to. And if you want to hear a little bit more about that and maybe get some more insight into what goes on in these videos and some of the behind the scenes and the some of the hidden avenues and the extra detail, you can maybe become a patron of this channel, because patrons will get these bonus videos. And so the bonus videos will be there coming out within a couple of days of the main video, and they will just add a little bit of extra detail and flavor. So in this extra video, just so you know, I'll be speaking a little bit about another kind of modulation scheme that you can use instead of PWM. And this is a modulation scheme called PDM, pulse density modulation. And for a bunch of reasons, it would have been cooler to use that. And I did in fact try, and I ended up sort of failing on that for a different reason. And yeah, I'm going to go into some more detail about that and why that's really cool in the bonus video. So maybe you'll join. If not, I hope you enjoyed this video. If you did, and you don't want to become a patron, please just share this with someone else that you think might find it interesting. You know, I'm really looking for other kinds of nerds who find this kind of stuff fun and interesting. And, you know, if you're one of those and you know more of those, spread the word. Let someone else know about the videos. Alright, thanks for watching. I'll see you next time.